So, hi everyone. My name is Jackson Vanover. I'm a graduate student at UC Davis, and I'm here today to talk about our team's work on discovering discrepancies in numerical libraries. And this talk's going to appear at ISTA in July. So, apologies, the target audience is more of a general software testing audience, so some of the preliminaries might be a bit obvious, but bear with me. So, to start, we'll start with the question: how do we know if a numerical result is correct? And we'll give an example here. Say we are using the NumPy library and we initialize this matrix with those values all being 132 and some change, and we take the mean. And at this point, we sort of have an intuitive idea. We have an intuition about what the result should be. It should be that 132 and some change, that exact value, since all of those are the same. But we see this and we know that there's an error. There's something that's not lining up. But the question is more interesting when we pull out, say, a function like the anger function from the JMAT library. We give it this input, we get this output. We don't know, we have less of an intuition about whether or not this is correct, right? Which brings us to the motivation here, which is the fact that test oracles are hard to find. Now, in this domain, right, one of those possible solutions, like Daming was talking about, is using high precision, and he talked about some of the downsides, so I won't go into those, but it merits asking for an oracle-free approach. And so here we'll offer one potential strategy, which is to identify other functions that implement the same analytical function, give it the same input, and look at the outputs and look for a numerical discrepancy. And in this case, we view one. We can see that JMAT is clearly the outlier, and that sort of points to this anger function implementation not being quite correct, something suspicious. And so really what we're talking about here is differential testing, right? And in this case, then the problem overview, what we're concerned with is implementing such differential testing, but in an automated manner and for numerical libraries. And we've identified 3 challenges in doing so. The first of which is extracting signatures, synthesizing drivers. We want to extract signatures that are the target of our testing within our scope. And we want to synthesize drivers because we have to execute those functions. We want to automatically discover function synonyms, and we define function synonyms to be function synonymity to be an equivalence relation that partitions the set of functions into equivalence classes. And this is non-trivial because documentation can be lacking, function names can be misleading. So it merits another approach besides just manually constructing those classes. And lastly, we want to identify meaningful discrepancies because not all discrepancies are indicative of buggy behavior, and that can be due to the inherent imprecision in floating point numbers, different choices with regards to implementation with like branch cuts and function polls or error handling. So we need to have a mean of triaging discrepancies. And so here we see our solution to this problem. This is FPDiff. It is an end-to-end tool for automated differential testing of numerical libraries, and it takes in the source code for the libraries that are being tested, puts it through these 3 components here that we see depicted, and ultimately generates a set of discrepancies. And these 3 components that you see here actually address those 3 challenges that were outlined on the previous slide. Today's talk is actually just going to focus on challenge 2 and 3. Challenge 1 is dealt with in our paper, which there will be a link to at the end. So challenge 2, which is finding function synonyms, this function classifier will conduct multiple evaluations over a series of elementary inputs that it also takes as input. And we define these elementary inputs to be inputs for which we expect these functions to exhibit well-defined behavior and ultimately generate a characteristic vector from these multiple evaluations. So to give an example, here we have a set of elementary inputs, and for our experiments, we generated those randomly and uniformly between 0 and 3. We got drivers in the left column. We have all our characteristic vectors in the right column. And as we evaluate all of these drivers over each of the elementary inputs, we populate our characteristic vectors. And then ultimately, function synonyms are going to be the drivers corresponding to the functions that have the same characteristic vectors. And here we see highlighted in yellow a subset of the equivalence class that was used in the example previously, representing regular cylindrical Bessel functions. So these equivalence classes are then given to the differential tester. The differential tester takes also as input adversarial inputs, which are intended to provoke divergence between those function synonyms that we've discovered. These can come from a bunch of different sources. For our experiments, we used test migration inputs from each of the libraries. We used inaccuracy-inducing inputs found by a modified version of the S3FP tool. And we use special value inputs like nan and infinity. But you can use whatever you want. It'd be interesting actually to use some of the inputs found by like Daming's tool, for instance, to see what sort of discrepancies we can find. But here's an example using that equivalence class of regular cylindrical Bessel functions and that input, which was a test migration input from GSL. We see that discrepancy that we saw before, and the differential tester will identify it as such, and we'll assign it a category. And this categorization, we provide 6 categories based on characteristics we observed in the discrepancies. And this is one of our contributions in the paper. I don't have time to go through all of them now, but suffice to say that they're organized higher numbers being corresponding with more severe discrepancies that are more likely to indicate buggy behavior. And in this case, this is a category 3 discrepancy, which is an inaccuracy. So our evaluation, let's talk about the function classifier and how well it finds function synonyms. It generated 310 mappings between function synonyms with a 95.8% precision and a 79% recall. Ultimately, this resulted in 126 distinct equivalence classes of special functions that represented almost 500 of those special functions across GSL written in C, JMAT written in JavaScript, and MPMath and SciPy written in Python. We calculated the precision and recall manually, and the precision was affected by the choice of elementary inputs. So there were about 4% of them, the mappings that were discovered would diverge for negative inputs, which were not used as elementary inputs. And the recall was mostly affected by the capture rate of the extractor component that came before the classifier, which is to say that a more complete set of drivers given to the classifier would generate a more complete collection of mappings. And then we have our differential testing component, and we want to know how well it found these discrepancies and if it could figure out which ones were meaningful. We generated 655 unique discrepancies, and these were reduced by about half to 327 based on the assigned discrepancy category, and these we inspected manually. We found 150 of those to represent reportably buggy behavior. And in particular, those 150 discrepancies represented 125 unique bugs. We reported all of these to the library developers, and to date, we've seen 30 fixes. 9 were found to be previously known, and 25 were acknowledged, but no fixes yet. So I just want to conclude then with just 3 examples of discrepancies that FPDiff found. This first one is a category 1 discrepancy, which were the discrepancies that were dropped from the complete set of 655. Category 1 discrepancies are not reliably very buggy. They're not as severe, and they sort of represent these cases where library developers made different choices with respect to the implementation. So here we see a test migration input from SciPy, and as a result, GSL and SciPy show that they're not supporting this particular portion of the domain, and the nan and the domain error are documented in the documentation. But JMAT and MPMath do support it, and they return a complex number. So not a bug, but illustrative of different choices made by library developers. The second one is a category 4 discrepancy for an equivalence class of the Hurwitz zeta function. And this is a special value input that prompted this, an infinity in particular. And we see that these libraries don't agree on the asymptotic behavior of this function. Combine that with the fact that JMAT supports limit evaluation elsewhere in the library for its special functions. This resulted in a report being filed, and we were able to suggest the proper behavior just by looking at the consensus in this equivalence class. And then the last one I want to talk about here is an inaccuracy-inducing input caused the discrepancy here in the equivalence class of the polygamma function. This is a category 2 discrepancy, and here we see that this input, which was generated by S3FP, maximized the error between those first 2 function synonyms there, the GSL and the MPMath one, and we can see that in the outputs there that discrepancy. But what was more interesting was the fact that when we applied this input to the rest of the equivalence class, we observed further that there was a discrepancy between MPMath's 2 implementations, one of which returned a complex number. So this single discrepancy resulted in 2 reports. So in conclusion, to wrap it up, here we've proposed an approach to discovering numerical bugs that's Oracle free. It's implemented as the tool FPDiff. and it utilizes function evaluations over elementary inputs, which we found to be an effective means of discovering function synonyms. And in the paper, we proposed a categorization of numerical discrepancies. The takeaway from this talk is that some categories of numerical discrepancies are more likely to be severe than others. And ultimately, we found 125 unique bugs. And that's my talk. Thank you very much.